Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and I'm here with John Wise, Product Line Manager for Beamforming ICs at Analog Devices. Welcome, John.
Hi, Pat. Thanks for having me today.
So the IEEE Phased Array Conference in Waltham, Mass. Recently wrapped up, and ADI was at the event. What did ADI present there?
Well, it was a very good show for ADI. It's been 3 years since we participated in the show, primarily due to COVID, and we were really excited about showing our latest contributions to the phased array community. We had several papers that we presented. One was discussing flat panel ESAs for SATCOM. Another paper talked about digital beamforming in LS and C bands. And lastly, we did a paper in conjunction with Keysight Technologies in discussing design, development, calibration, and test of Ka band phased array platforms. In addition to all this, we just recently sent a press release out announcing our collaboration with Keysight in the area of phased array to basically enhance the ecosystem to help expedite our customers from design, test, and calibration of phased arrays. So you can see phased array it's an area that ADI, especially in the aerospace and defense group, are heavily investing in.
Yeah, I did see that news with Keysight. Looks like a great collaboration.
Yes, yes, it is.
And it looks like you guys are addressing a lot of different applications. What are the major trends that you're seeing in the markets for phased arrays?
Yeah, so within the aerospace and defense group, there's really three areas that we're addressing here. So SATCOM is one area that we're addressing, and as you can imagine, with the proliferation of these LEO constellations, that's really driving the need for phased array. Not only on the terminal side, which we're working on, but also in the satellite side as well. So we're developing solutions to address both ends of that spectrum. And as you can imagine, as the data rates start increasing, there's a need to get up higher in frequency. So we're seeing the trend from KU to Ka band, and even we're working in Q and V band as well. We're also seeing areas in radar that's expanding. And one of the interesting applications in radar is in these Earth imaging satellites where they're using synthetic aperture radars to do mapping of ground terrain and environmental measurements of the Earth. And lastly, many people are looking at software-defined apertures, broadband arrays, where you can basically build one array that can serve many different applications. And with these requirements, we're doing a lot of investing in true time delay to cover 2 to 18 gigahertz.
And how is ADI addressing all these different applications?
So while these applications, they seem a little bit different, they all have certain IP requirements. So we're developing an IP portfolio that helps address these, and we're targeting like three main areas in there. One is low power dissipation. So one of the things that we're doing in our beamforming ICs is that we have pivoted from using, say, like active components to do the beam steering to more passive technologies to help lower the power dissipation in our beamforming ICs. Also, high levels of integration. And as you can imagine, as you start increasing in frequency, the lattice pitch starts to reduce in size, causing more and more functionality to be placed at the beamforming level. So we've developed multi-beam topologies for this, as well as very sophisticated digital definitions, which allow things like beam hopping, raster scan, and that functionality to be done at the beamforming level. So that helps. That helps with updates and things like that. And also a wide instantaneous bandwidth. So I mentioned in these software-defined apertures, the need to be able to cover very broad bandwidths, but also even in the area of SATCOM, as data rates start increasing, that's going to force the beams to be wider in bandwidth, causing more issues with beam squint. So again, we're leveraging our true time delay technology to help address these wide instantaneous bandwidth needs.
So what solutions has ADI developed to address these various applications?
So to date, the parts that we've released the ADAR 1000. That was our first commercially released beamforming IC. That's a 1x4 half duplex chipset. basically covering 8 to 16 gigahertz. So it's very well suited to address radar applications. We were also designing a family of TR modules that accompany that. So depending upon the application, you can pick a TR module that has the suitable output power and noise figure for your application. Last year, we introduced the ADAR 3000 and 3001. That's a Ka band full duplex chipset, where the ADAR 3000 covers 17 to 21 gigahertz, and the ADAR 3001 covers 27.5 to 31 gigahertz. This is an example of a very highly integrated beamformer. It's a 4-beam, 16-channel beamforming IC. It's designed to support not only the satellite side of these SATCOM links, but also can be used on the terminal side as well. So it has this dual functionality built into the device, and it also has a very sophisticated digital definition in it. And most recently, we just introduced the ADAR 4002, which is an extremely wide band true time delay unit, which covers 500 megahertz to 19 gigahertz.
So can you tell me a little bit more about that latest solution?
Yeah, sure, Pat. So the ADAR 4002, as I mentioned, it's a brand new product. It covers 500 megahertz to 19 gigahertz, and it's a single channel true time delay part. In the part, you have a 6-bit digital step attenuator along with a 7-bit time delay. The time delay, it has up to 508 picoseconds of true time delay, but that can be switched to 254 picoseconds and still retain 7 bits of resolution. So what this gives you the ability to do and the flexibility is that at lower frequencies where you might need a wider time delay to create a 360-degree phase rotation of the signal, you have that ability in that mode at 508 picoseconds. But if you're working at a higher frequency and you need increased resolution, you can switch to 254 picoseconds and go from 4 picoseconds resolution down to 2 picoseconds resolution. In addition to this, there's also internal memory in the device where you can store 64 beam states. It has a sequencer function where you can rotate through these beam states in any prescribed order with very, very fast update rates. But in addition to that, since it's a very small device and a single channel device, we've also implemented a daisy chain feature. So if you're using this across an array and you need to load beam weights in, you can just do that serially across several of these ADAR 4002s, to load in the data into each one of those. And the other aspect to this is that it's an extremely small device. It's 2 by 3 millimeters. So from a swap perspective, it's a very unique solution.
Wow, that's quite a wide variety of support for that applications. Well, John, thank you for talking with me today about phased array technology and analog devices solutions from this area. You can find more videos at videos.microwavejournal.com. Thanks for watching and join us next time on Frequency Matters.